Well, thank you very much to the organisers for inviting me. It's been a wild and crazy trip over the last 4 days, and at the end of the first day I was going to sneak out of the hotel in the middle of the night and go back home because I was so confused. But the subsequent days have really got me thinking again about some aspects of emergence, and so I really appreciate that. All right, so here's just the outline of the talk. I just want to present some results from the survey, which many of you kindly filled out. And then I'm going to give you what I think is a very sort of broad scope survey of what some characteristic features of emergence are that are drawn from scientific and philosophical literature, and then just discuss two important ways that emergence can occur, which are synchronic and diachronic, and I'll explain those. And then the second part of the sixfold taxonomy will be in section 3, and then I'll finish up with a brief, I think, sort of slightly challenging view about what may or may not be true. All right, so if anything has happened in this conference, it's a realization of this, that trying to get a single unifying concept of emergence at this point in time, I think, is not a good idea. That you've seen there are multiply motivated different concepts of emergence. They seem to be used differently in different fields, and they are essentially different from one another. And I hope if we can all keep that in mind, it would be a good thing. The word emergence is a magical word. You know, people are drawn to it. They like to use it in preference to some other things which may be slightly more appropriate, but it's not going to go away, and so we'll have to live with it. So here are two different ways that I found people approach emergence. The first one is that they like to look for general principles of phenomena that are exhibiting emergence. The second way, and this is a bottom-up way, is to identify specific examples of emergence. We've seen lots of those in the last few days or so. So, got 36 responses to the survey. Here's a breakdown of the areas which people were in. There's a lowly humanities figure at the bottom there. Guess who that was? Okay, so if you look at this, overall, you guys are completely evenly split between thinking that you should start with general principles as opposed to starting with specific examples. And here's a breakdown for the 5 scientific areas. Chemistry is also evenly split. Earth planetary sciences are evenly split. Life sciences are pretty evenly split. Then you get over here to the physicists and the astrophysics. They don't like general principles at all. They want to start with specific examples. And I'm not going to conjecture why that is. I would love to hear from the astrophysicists here what it is that they don't like about the general principles. And then those of you who work in complex systems, it's not as strong as it is here, but there does seem to be a kind of bias there with specific examples, which is fine. Okay, so here's a rank ordering of the possibilities for examples of emergence. And I've aggregated the results, breaking them down into the specific scientific areas would get numbers much smaller than they already are. So here's the example that a lot of people like, and I suppose given the nature of ELSI, that's not surprising. Okay? Here's one that is interesting. I don't like this as an example of emergence at all because it's got that magical content to it. And despite advantages in neuroscience, we still don't understand consciousness anywhere enough to really say something informative about what the heck is giving rise to it. But still, you guys liked it. Flocking and schooling was pretty popular. So was phase transitions. And then we come down to a sort of motley collection of examples there. On the other side, this is going to work. Whoops, let's stop working somehow. Let's just, oh, there it is. Okay, good. Okay, so these are rank ordering of examples that the respondents were pretty clearly thought were not examples of emergence. Now, if you remember the previous slide, here, is an interesting thing. A lot of people previously thought that traffic jams were an example of emergence, and phase transitions certainly were, but a number of you think that they're actually not. Very unpopular one for non-emergence is time. If you talk to people who work in quantum gravity, they have somewhat different perspective on that. So one of the things that I hope you can see from this is that there's a certain amount of disciplinarity here. And I would like to use this to suggest that it might be more profitable if you want to make progress in emergence to really just talk to other people in your own area and see what it is that you generally find is the commonality in what you consider to be emergence. And then when you start talking to people in different areas, you'll probably find that they have different criteria. But at that point, you've got something that you can discuss. So this is not scientifically respectable survey, but I think it is suggestive of a number of things. Let me do this manually. All right, so what can we take away from this? It's a real problem. Think about causation, which is something that is widely discussed in both science and philosophy. Everybody can agree that there are core examples of causation. Right? You look at the rock breaking the window, that's something that if you claim is not an example of causation, you've got a problem. Now, I have to say, when I was a small boy, I broke a window with a rock. I confessed to my mother that I'd thrown the rock, but I'd said, well, the window just broke. It wasn't my fault. But mothers are expert on cause-effect relations. Forget it. Wait until your father gets home and all that kind of stuff. In causation, we've got this nice set of examples. Here's another one. This is a cause, obviously not the only one, for what's going on here. That doesn't mean to say that there aren't significant issues in trying to identify at what level this is causing that. But for somebody to deny that there is a causal connection between this stuff and these biological processes here would be absurd. So it's a big advantage that analyses of causation have, because undeniably giving a theory of causation is not easy. But people can always revert to these canonical examples and use it to bolster their account or for somebody to show that it's false. Because emergence doesn't have that, it's so hard for somebody to convince somebody else that this is actually a good theory of emergence, because there's no agreement on the examples. So that's the takeaway from the first part. Okay, so here's the second part. An important thing about the concept of emergence is that logically it's relational. Now, ordinary language is very deceptive here, because we all, including myself, say that thing there is emergent. But of course, what it is emergent from something else. So that's an important feature to always keep in mind when you're talking about what it is that this thing here has emerged from. Second characteristic feature, which Yuko mentioned, is that emergent entities are novel. Third characteristic is that emergent entities have a sort of autonomy. They become independent of the things that they've emerged from. And then, common feature, but one I think is, I'm going to argue, is not always required, is that there's some element of holism in there. All right, so why are there these different conceptions of causation? Well, that's the topic of a very long discussion, but I just want to suggest one reason why these differences appear. Those four criteria that I give you are actually schema. If you think about Schrödinger's equation, and you've got the Hamiltonian that you have to choose, right? Schrödinger's equation is just a schema. In order to actually apply it to anything, you've got to give a specific form for the Hamiltonian. Similarly, when you talk about novelty, you have to be very clear about what it is that you think is novel in the system. If you want to say that this thing has emerged from that, you've got to be very specific about what things it is that this novel phenomenon has emerged from. One thing that happens is that you've got a set of closure conditions on a domain, and you come across a phenomenon for which those closure conditions don't apply. You've gone into a new area. Now, different closure conditions are going to apply to different scientific domains, and they can fail in different ways. And I think one reason why you get these differences of opinion is that the closure conditions for different areas are different. So here's a couple of examples. Compositionality is an important part of reductionism. The inverse of decomposition is something that you would expect with reduction. When you get a failure of decomposition, and quantum entanglement, which gives rise to holism, is a great example of this. There you've got a failure of closure conditions for reduction. You've got to go to something distinctively new. Sometimes the closure conditions for representations fail. You've got a group of representational apparatuses that work really well in your field, and then you come across a phenomenon for which they suddenly don't have the correct representational power. Here's a very simple example, right? The concept of flocking just doesn't apply to individual birds. I mean, that's obvious. So you've got to invent a new term, which was already in the language, but that's the way that you have to represent the phenomenon you're dealing with. Theoretical underivability, either in practice or in principle, is something that's going to take you into a new domain. There are undecidable states of physical systems where undecidable is in the usual logical sense. Or, of course, notoriously, you've got high complexity, MP complex systems or something like that, and you have to switch to a different way of representing and predicting those phenomena. All right, here's another possible set of differences, and excuse me for pointing this out, because I know you'll realize that this difference is there, but sometimes it's worth reminding people of these things. You can talk about emergence as occurring out there in the world, or you can talk about emergence as occurring within some system. Maybe it's a computational system, maybe it's a model system, it doesn't matter. But these two things need to have bridge principles between them. And here are a couple of examples of bridge questions. Suppose that you've got some mathematical idealization. For example, you've got to have an infinite population in order to display the emergent phenomenon. How are you going to justify that for a natural system? If you can't, then you've got to restrict your claim of emergence to the theoretical model. If you can, great, then you can justify the applicability to the real system. Second, models are almost always oversimplified. Can you actually transfer those things to natural systems? And you guys, of course, work with this all the time. But those are things that we all have to be careful of in moving between those two possibilities. All right. Here's something which I'm sure you're familiar with, but maybe the vocabulary that you use is different. And the differences between what we philosophers call synchronic emergence and diachronic emergence. And here's an example. Right, so you're all familiar, I'm sure, with the basic architectural features of neural nets, and here's a much simplified representation of deep neural net. Usually the number of layers there is much larger. But here's the important thing. The activation levels in each layer are not individually at those nodes the things that give you the representations in neural nets. The representations are distributed over activation levels in that particular layer. But that distributive representation exists at the same time as the individual activation levels of those nodes. So up here you've got the distributive representation, sort of down here at the same time you've got the activation levels of the individual nodes. Given that pretty much everybody agrees that whatever is going on in individual nodes here is not usefully representational, you have to go up to that higher level, and that's where you've got an example of synchronic emergence in some representational sense. Okay? Here's an example of diachronic emergence, and just a little caution, these two things can occur together in the same system. So I just want here to focus on the diachronic feature. As you all know, slime molds often considered to result from self-organizing processes. Those self-organizing processes occur over time, and the individual spores end up with that kind of organizational structure. But there's a definite dynamic diachronic aspect to that. Now, so how can we capture this? Well, this is a conjecture. When I arrived at this conference, I believed in this, and the conjecture wasn't there. I put this in last night. I think that if you remember back to the four definitional concepts, and let me just remind you what they are, right? Developing from novelty, autonomy, and holism. I think for diachronic emergence, the first three conditions there are each individually necessary. It's got to have novelty, you've got to have it emerging out of something else, and so forth. And here's the conjectural part. I think that they're jointly sufficient for emergent. But we can discuss that if you're not happy with that. For synchronic emergence, differently interpreted, the first three conditions are also individually necessary, so novelty, emerging out of, and so forth. But generally speaking, you're going to add something else, and that's that important feature of holism in order to get those things to be sufficient. But here's, in red, the important thing. A lot of systems are going to exhibit both of those, and just got to be aware of that. So that. All right, so just a little bit more detail about a couple of examples here. So here's a somewhat better representation of convolutional neural nets. And the thing I want to point out here is that at least according to, some traditions, if you map back the representations that occur at these different layers, you map them back onto the input space. You can identify in successive layers things like, arcs of curves. You can put those together into edges. Here they've got complex shapes, and then you assemble those into objects from which the softmax classifiers at the end there are going to give you the highest probability of the thing that has been inputted here as being a flower. Now, one of the interesting things is that if you actually believe those reconstruction efforts, you've got compositionality with these successive layers. You're building up a representation at this level from elements at this level. That isn't probably generally true. So that's why the business of explainable AI is of such concern. But the general point here is that these distributive representations here, here, and here are not local. There's no so-called grandmother node here, which is representing, or here a flower node, which is representing a flower. So that's a synchronic aspect of it. But of course, the final representations down here are emerging across time. So that's an example of both. Let me skip this because I already explained this. So here's a second one. Remember, this was fairly popular. Bird flocking. The formation of the flock or the reformation of it after disturbance is definitely a diachronic process. But the coherent shape of the flock, the one that prevents predatory success in many cases, is got the characteristic of being novel, it's holistic, and it's autonomous because it doesn't matter which specific birds are in the flocks. Right? Could have been a completely different group of birds, and they would still have formed the characteristic shape for that species of bird. All right, so part 3. Here's the other part of this taxonomy that I'd like to suggest to you. And Yuko mentioned some of these things. Epistemological emergence. So the reason I'm sort of emphasizing this is because I think it's very helpful to keep these 3 kinds separate from one another because they really are distinctively different. So epistemological emergence tells us something about how our theoretical apparatus is limited. It doesn't give you all of the information about the system in certain places that you would have hoped for. And here's something I think that is enormously important and actually goes back to the heyday of what was called British emergentism in the 1920s. You've got an epistemologically emergent phenomenon when your theoretical apparatus fails. Remember, closure condition fails. Here, the closures of the theoretical derivability has given way. How are you going to find out about that phenomenon? Well, you've got to observe it. Now, one small caution. Once you've observed it, and let's assume that you can observe other examples of that same emergent phenomenon, then you can start building up new theoretical representations of this new thing that you've started observing. And you then introduce that new apparatus in there. But before you had observed that thing for the first time, then the existing theoretical apparatus was simply inadequate. And that's where surprise comes from. I don't like the idea of surprise as somehow being all you need. I mean, if it was, you go to a magician's show and bingo, you've got a lot of emergent phenomena, and that's far too weak. So epistemological emergence certainly has surprise coming along with it, but there's certainly other features. Why do we come across, or why do we need epistemological emergence? Well, one reason is this too great theoretical gap between levels. That's why people think that consciousness is emergent. You've got conscious phenomena, you've got the level of neuroscience, there's still a huge theoretical gap between those things, and so people consider consciousness to be emergent. You've got the undecidability of theory sometimes, you've got the high computational complexity, and then famously, nonlinearity is something that produces predictive problems, and so you have to move to something else. Here are a couple of examples. We had talked this morning about Schelling model. Just a small local point of interest here. It's usually called the Schelling model. It should really also be giving credit to somebody else. A man named James Sakoda, who was born in the United States. His parents were Japanese. He lived in Japan for a while. And he, in fact, in his 1949 PhD dissertation, described a generalization of what Thomas Schelling published in the 1970s. Sakoda, in fact, published in the first issue of the Journal of Mathematical Sociology his own formulation of this, and Schelling published in the second issue of the Journal of Mathematical Sociology. But Schelling gets all the credit for this. Now, that's fine. I mean, Schelling had a genius for distilling the essence of problems in a way that was tremendously useful. But if you're interested in why some people get credit for important discoveries and other people get forgotten. I would strongly recommend, although this is a very long article, René Hagelman's article in the Journal of Artificial Societies and Social Simulations. But the point for us here is that you start from a random arrangement of housing, for example, with different theoretical thresholds. Over here, you get pretty extreme forms of segregation. Traffic jams, of course, there are representations of traffic jams using differential equations, shock waves, and so forth. But if you want to do this at the level of individual cars, it's very hard to do this without simulations. You have to wait for the simulations to work their way out. Right? So, second type, conceptual emergence. What you have to do in order to get predictive efficiency is to reconceptualize the system at some different level, usually at the macro level rather than the micro level. Conceptual emergence is certainly compatible with ontological reduction. It's compatible with theoretical reduction in principle, but it's not compatible with theoretical reduction in practice. Once you've got that, a new conceptual apparatus is really irrelevant. Okay, so conceptual emergence is not much talked about, but I think that it's worth keeping in mind. And in fact, those of you who are familiar with Philip Anderson's famous More is Different article, that's in fact conceptual emergence that he is talking about there in his paper. You get conceptual emergence because you get holism. And as I mentioned, you know, flocks are vocabulary that don't appear at the level of individuals. Functional properties are interesting. At our breakout session last night, money was suggested as an emergent phenomenon. Why is this? Well, money is what's called multiply realizable. What's in your bank account is encoded in electronic bits. You go to an ATM, converts that into the paper currency that comes out and you can use in your local coffee shop. They're both money, right? And that concept of money is autonomous from the particular form that money is actually being stored in the present time. All right, so here's some examples of conceptual emergence. In order to talk about liquidity, you're talking about bulk properties of water. Liquidity doesn't apply at the level of individual H2O molecules. Computability is a good example. You'll know that computations can be carried out on radically different kinds of things, biological systems, silicon, a lot of other kinds of things. That's another example of multiple realizability, and the third one is money. Okay. Last thing, ontological emergence. That's where you've got genuine novelty in the world. And I think the first, second, and third conditions for emergence are satisfied by real properties out there in the world. Here are some characteristic features of ontological emergence. You've got in principle irreducibility. There's something out there in the world that is stopping us forming theories that are completely satisfactory at all levels of currents of phenomena. What you often get is also the appearance not just of new properties, but of new laws. And I'll say something about that in the last section. I think it's the most difficult type to motivate. I think it's out there, and if I had more time, I'd give you a lot of examples of it. But a lot of people, I think, for understandable reasons, shy away from that. We talked about downward causation. This is seen to be one of the big problems in ontological emergence. I think it's actually a solvable problem, but we'll... okay, so let me just do... So here's the six-fold classification with some examples there. And let me just quickly finish up with the last section. The examples I gave you of synchronic and diachronic emergence exhibited both kinds. So the question is, are there pure examples of diachronic emergence? I think that there are. Here's an example. Take the standard model. Now, within that, you've got muon decay into those three types of other elementary particles. Muons are elementary, and those three decay products are elementary. Because they're all elementary, that is, they don't have constituents, that process of decay is not a decomposition. You've gone from non-composite particle to other non-composite particles. So instead of a decomposition, it's a transformation. So that famous slogan, the whole is more than the sum of the parts, just doesn't apply. There are no parts in muons, but you've got something that is distinctively new. And that's where you've got the three conditions satisfied, and importantly, holism is just an irrelevant concept here. Here's just a final question I want to leave you with. Since at ELSI you're looking at the development of the universe, Earth, life, and so forth, of course, methodologically, you have to assume that the laws that we think apply to current systems can be extrapolated backwards in time. Maybe that isn't true. And if it isn't true, then things like grand unifying theories are going to have to be brought to bear to try and get some connection between those different features. And this is the last slide. I think this is a possible example. So, as astrophysicists, of course, will tell you that out there was a order of succession. Leptons came into existence after baryons, and that neither of them are present in the pre-baryogenesis period. There's conservation of lepton number, there's conservation of baryon number law. Unless you believe that those laws were there, lurking, waiting for leptons and baryons to actually come into existence, then it looks like those conservation laws actually came into existence themselves at some point in time. So thank you for bearing with me. I've run over time a little bit. I'm sorry about that, but be glad to answer questions.
Thank you, Paul. That was wonderful. I think you gave plenty of conceptual distinctions that could clarify a lot of the ambiguities and confusion in past days. So let's first take some questions from the audience. And meanwhile, you can also use Slido, of course. Everyone? Okay.
I don't really have a question, but I did just really want to say thank you, especially for the first part of that talk. I feel that you expressed that so clearly, and some of those were points I'd really been struggling to express in the discussion session. So I just think it's so enormously helpful to have done that. So
thank you. I don't always get things like that. So thanks.
And I second what he said. A really, really helpful talk. At the one point, you were discussing how a property may seem emergent if there is a larger gap in theory between what is known now and what is emerging. And so does that mean that whether or not something is emergent could depend on the state of human knowledge?
Absolutely.
And that's okay? So emergence is not an intrinsic quality necessarily. It's part perception.
Yeah, so that's why ontological emergence and epistemological emergence are so very different. Okay? Epistemological emergence is directly a product of what we know, and unless you're in an area where you've got unpredictability in principle, and in some special cases you can prove that's present. But most of the time, we think that something is emergent just because we don't know enough about it. Which is why, I personally find ontological emergence much more interesting, but it's much harder to show conclusively that something really is an example of that, because theories change and science moves on. So.
Yeah, I know it's. I'll just repeat what the two previous said and what he was indicating, and I guess I was hinting at in the discussion before. I think that it would have been really helpful if this had been the start of the conference.
Well.
So because that would have, a lot of the confusion would have gone away, and we would have been much more productive in talking about emergence in the different fields, because we could have been much more precise in this conversation. So, anyways, I get that was a great talk.
Stuart, do you want to?
Yeah, I might have missed something here, but in the muon decay case, if that is emergence, but you just do the reverse, what is the reverse?
It's an interesting, So, those decay products, as many of you know, only exist for a very small amount of time, and then they recombine back into muons. So we had a discussion in our breakout group last night about whether irreversibility is a requirement for emergent phenomenon. And so people cited the case of phase transitions, right? So those are reversible, but if you believe that phase transitions are genuine cases of emergence, then reversibility is okay. And so here, you've got another example. But it's interesting because, you've got those three decay products, but they're not there in the muon when they, the process gives you back what you get. But yeah, is it okay to have reversibility?
No, I mean, yeah, it might be. To some extent, emergence requires some degree of dissipation to be going on somewhere in the system, perhaps.
And here's maybe where sort of disciplinary differences are coming in. I mean, presumably those of you who are interested in the emergence of life don't kind of want the tape to run in reverse. That's not what you're interested in. Right? But with if there are examples of diachronic emergence in high energy physics, maybe you just got different criteria there. People are looking for different things.
If I can briefly follow up on this muon example here.
I'm sorry.
I think this is a case of multiple levels of emergence, which makes it so interesting. A muon decaying in other particles, the muon is an excitation of a muon field, and the other particles, on one level of understanding, are excitations of other fields. But then, in the current best picture, these different fields are examples of specific angles on a unified theory which combines all of these fields. So in that sense, the particles, one particle becomes another particle on one level, and in another sense, an excitation of one field triggers an excitation in another field. And on yet a third level, there is one field where the different excitations trigger each other. And there you can sort of say that the whole is more than the sum of its parts. The parts are whatever the deepest underlying field is. But then you go deeper to the unified theory of everything, all the four forces, which probably entails that we go beyond space and time, and they become emergent properties. Most physicists working in that area would agree with that. So I'll stop here, but I think it's a beautiful example of the interplay of different levels.
Yeah, thank you for that. I feel slightly uncomfortable about that example because the particle talk is maybe not to be taken completely seriously, but after all, I mean, this is how people who use the standard model talk, and it may be yet another example of the theoretical representations that we have as they get more sophisticated in a way, make this one go away, but it'll reappear in a different form somewhere down or up the hierarchy. But thank you for that.
So, Paul, I don't want to be a pain in the ass, and I don't know if I feel a responsibility or if I just can't help myself. I would like to make a request that some of these things not be taken as closed matters, but remain things to think about, and a certain request for conceptual hygiene, or like category hygiene. So, I mean, you can do what the Oxford English Dictionary insists we should do and say that emergence includes anything that anyone can refer to with the word emergence. And it has the benefit of being fair. It has the difficulty that many uses don't do work for you. So if Tony Jaa comes through the door, I can say Tony has emerged from the lobby. That gets used. It's helpful for me to tell you where Tony is, but it doesn't actually solve a scientific problem of understanding, right? The use of emergence that I am familiar with, which is kind of the old one, it didn't matter what we called it at all. We had a whole basket of phenomena that were all not obvious and that all turned out to depend on each other. And we worked them all out, and then we said, okay, we can't give a semester lecture each time we mean to refer to it. Let's give it a name, but we remember the name stands for something. The idea that entanglement is emergent in any sense, that feels to me like entanglement is emergent in the same sense as spooky action at a distance from the Pauli principle is emergent. I would call that an artifact of bad language, which has nothing to do with the world. Entanglement can also be expressed as the fact that certain things that we might have imagined were in the state space of the universe are not in the state space of the universe. And the fact that we imagined wrong is not a scientific concept in the same way as emergent long-range order is a scientific concept that does work. I worry also about the particle physics example, where if I have scattering matrices and I have quantum field theory, and I want to discuss things at the level of quantum field theory, what problem is left unsolved or unorganized, which is solved by applying the word emergence to the fact that muons can decay? I don't see that doing scientific work in the same sense, and I feel like for a productive conversation, a good thing to have in it is the question, what work was left undone that having this term does for you?
Yeah, I'm actually very sympathetic to that point. And the reason I started out with that contrast between causation and emergence is that we, despite the difficulty of, epidemiologists have tremendous problems in identifying specific cases of causation, but we have a reasonable amount of control over how that word cause is used. Right. Emergence, as you very nicely pointed out, has just escaped us. I mean, people use it in a wide variety of ways, some of which have nothing to do with the other uses. So, if somebody like you suggests to me that we should just stop using the word and use more specific terminology like self-organizing processes or something, that would probably be helpful. But here we are. I mean, we're at a 4-day conference with, over 100 people, very serious researchers who want to use this term. All right. Yeah. So I don't know how what to do with that. Do you see what I mean?
Entirely. As a Belgian friend of mine says, it's a puzzle.
It's a puzzle. Yeah.
No, but my request was to leave things not closed as items to structured discussion going forward and to not pass beyond them too quickly.
Oh, I'm really sorry. That was not my intention in this talk. The sixfold taxonomy is one that I find useful.
Yes.
There's no question that given those 100 or more examples that came up in the breakout sessions, that some of them are not going to fit in here, right? So it's not going to work for everything. But I was hoping it was a sort of constructive place to be, and then we can move beyond that. So yeah,
I think that is affirmed that it is so.
Yeah.
Yes. Mm-hmm. Yes.
Yeah.
Okay, so we're running out of time. So last quick question. Let's take this one, the top one. Does the observation that our theories always tend to have gaps suggest something about a relationship between epistemological and ontological emergence?
Ooh. Sorry, who was? Oh, that's anonymous. Okay. All right. Theories always have, yeah, well, of course, I mean, theories, except in gross anatomy or something, you know, do always have gaps. The obvious relationship is that if there really is emergent, ontological emergence out there, then if you have a good theory of it, then there are going to be predictive deficiencies in that theory, because it's going to mirror a sort of incompleteness in the world itself. It doesn't go the other way, as we already discussed, right? The fact that now in early 21st century, there are things that look emergent to us from the perspective of our theories, of course, does not mean that in 50 years' time, we'll still be regarding those things as emergent. I don't like emergence. I mean, some of it is explainable, but others just, as I mentioned, seem magical, and that's not a good place for science to be. But the tremendous success of reductionism is going away. I mean, maybe it was the low-hanging fruit part, and the reason why it's important to consider emergence seriously is that reductionism is probably not a universally applicable way to approach some scientific fields. It's enormously successful in many areas, but maybe not in all. So I think there's an asymmetry between those two directions.
Thank you.